All right, chapter 3, derivatives of the inverse trig functions. There's really no good way to do these except to just memorize them straight out. Okay, so you memorized them once last year, so hopefully memorizing them again, if you've forgotten them, will not be too much trouble. So we're learning these just so that we can see the relationship between the original function and its inverse, and also the relationship between the inverse function and its derivative. So the derivatives are defined as a series of fractions. The derivative of the arc sine or the inverse sine is based on the chain rule, and so you just straight out memorize that it's 1 over the square root of 1 minus u squared, followed by the chain rule of du dx. This is assuming that the value of u is between 1 and negative 1. That's what absolute value less than 1 means. It means u itself is between 1 and negative 1, that it's not larger than that. Otherwise, the domain of inverse sine is violated. So in a similar way, in the blank space, I want you to put the derivative of the inverse of cosine. And the domain on that is the same as well, but it is so similar to sine. The only difference is that the numerator is negative 1. And then the rest of the derivative is the same, times the chain rule of du dx. Now there are really long proofs that if you got desperate and you couldn't remember, has to do with the Pythagorean theorem to prove the derivative of the inverse. But I think you're going to probably just be better off just straight out memorizing these. So that's the first pair. Anything with a inverse cosine, inverse cosecant, inverse cotangent, is just the negative of the other of its pair function. So that's the derivative of the arc sine. So just a quick practice on that. Okay, assuming here that 8x squared will always stay between 1 and negative 1. And so then that would tell you that dividing everything by 8 would give you negative 1/8 of x squared. And then taking the square root, which you can't do of a negative number. And so you have to shorten this up, and it has to be between 0 and 1/8. Okay, you can't, an x squared term always has to be positive. Could be equal to 0 also. And then we take the square root of everything. So x must be between 0 and the square root of 1/8. So that's the domain of this problem. Okay. All right, so back to finding the derivative. So dy dx would be 1 over the square root of 1 minus the quantity, 8x squared, quantity squared, and then times the chain rule on 8x squared, which would be times 16x. So I'd prefer that you wrote that as 16x over the square root of 1 minus 64x to the 4th. You don't have to rationalize. You don't have to simplify. You can just leave it like that. Any questions so far? Just stop me and wave if you do. Okay, let's look at tangent. The derivative of tangent has a domain of all real numbers, so we don't have any domain issues here. So the derivative of the tangent inverse is 1 over 1 plus u squared times the chain rule of du dx. So underneath that, you can put the derivative of cotangent. And it's going to be the same as tangent, just with a negative numerator. And then times the chain rule of du dx. And notice it's defined for all real numbers. So if we're going to practice just finding the derivative, y prime would be, because it's cotangent, it'll be -1 over 1 plus the quantity x squared squared, and then times the chain rule, 2x. So we're looking at -2x as our numerator and 1 plus x to the 4th as the denominator. Pretty straightforward. Derivatives of inverses are always pretty simple. They just have building blocks that you plug in. You just have to memorize them and make sure you know which ones have square roots and which ones have subtraction and which ones don't. So the last pair is the derivative of inverse secant and inverse cosecant. And we have a different restriction here this time, is that u, the absolute value, has to be greater than 1. So that means that u itself must either be greater than 1 or it has to be less than -1. So it's the complete opposite domain of inverse sine and inverse cosine. The derivative is defined as 1 over the absolute value of u and the square root of u squared minus 1. So in the similar pattern, you can develop the derivative of inverse cosecant, and that would have -1 as its numerator, the absolute value of u times the square root of u squared minus 1, and then the chain rule of du dx with the same domain restrictions. And so to finish up, we'll find a tangent line with the inverse derivative of 2x, inverse secant. The derivative, tangent line to the function, the inverse secant of 2x at x is 1. So let's make sure it's within the domain. So 2x must be either greater than 1 or 2x must be less than -1. And the implication on those then is that x must be greater than 1/2 or x must be less than -1/2. And x equals 1 falls within that domain, so we are fine to continue. So to find a tangent line, we need a point and we need a slope. And so we need to figure out what f of 1 is. And so we're looking at the inverse secant of 2 times 1, or the inverse secant of 2, which is equivalent to the inverse cosine of the fraction 1/2. These are based on reciprocal pairs, so since secant is the reciprocal of cosine, then the value of 2 can be taken as the reciprocal, and we have the inverse cosine of 1/2. So we're looking for a position in quadrant 1 on the unit circle that would satisfy the inverse cosine of 1/2, and that's going to be 1/3 pi. So there's my point, and now I need my slope. My slope would be f prime of x. So this will be 1 over the absolute value of 2x times the square root of the quantity 2x squared minus 1 times the chain rule, which is always the thing that catches people, of just 2. So now at the number 1, I can simplify. So I'll have 2 as my numerator over the absolute value of 2 times the square root of quantity 2 squared minus 1. So I can reduce, because both of those by definition are positive. So 1 over the square root of 3. So then my tangent line would be the point and the slope. So y minus 1/3 pi is my y value. The tangent is 1 over the square root of 3, which we don't have to rationalize. And then x minus 1. And you can leave your tangent line in point slope form. All right, less than 11 minutes. So that's a pretty short and sweet lesson.